Hello everyone. So the next type of problem is the frames. So again, the question is analyze the frame using displacement method. So there is a frame given here, and this is a frame wherein A, B, C and D are fixed, and A has a hinge support. Now, just by seeing the frame, you can make out whether it's a sway or a non-sway. So in this frame, you can see A is a hinge support. Okay, and at C there is a fixed support. So if there is a fixed support in the topmost member of the frame, then it is understood that it is a non-sway frame. Okay, because even if it has to sway, the fixity condition will not allow it to sway. Okay, so that's why here it is fixed. Okay, this is fixed. C and D and A is hinge support, so it's a non-sway frame. Okay, so again, as usual, what we used to do is we used to find previous steps, that is, you used to find the kinematic indeterminacy first. But what happens here is the kinematic indeterminacy will not hold good for frames. This formula, that is 3j minus r plus m, will not hold good for frames. So it is only acceptable for beams. So that's how what we do here is, just by seeing the frame, now we can analyze whether where there is rotation happening. Now you can see here, A has a hinge support. B is also treated as a hinge. C and D are fixed support. Okay, so at C, because there's fixed support, there is no kinematic indeterminacy. You cannot apply this here. Okay, it cannot move in any direction. That is, it cannot move horizontally, vertically. It doesn't have any rotation. Likewise, at D also, because of the fixed condition, it cannot move horizontal, vertical, or the rotation cannot happen. Okay, so A is a hinge support. That means it has reaction. Hinge means it has two reactions. That is, it cannot move horizontally, it cannot move vertically. So there are only two reactions, but still it can move in the third direction. That is nothing but the rotation here. Likewise, at B, it is also a hinge support. Again, the reaction would be it cannot move horizontal, it cannot move vertical. So it can move only in the third direction, and the third direction happens to be a rotation here. So just by seeing the frame, now this is done manually. Just by seeing the frame, you can uh, put this ki, that is ki is equal to 2 here. So here, this is the first displacement direction, first coordinate direction. This is the second coordinate direction. Okay, 1 and 2, that is at A and B. Okay, so now after this, once you find the ki and put the coordinate direction, next, as usual, find uh, moment, that is the fixed end moments. So the fixed end moments here is, again, in this AB there is no load, BC also no load. So there is only load in BD. Okay, now because there is a load in BD, only that portion, that is M MDB. Okay, MDB is equal to, from this end. Okay, always you should choose like this. DB is minus WA square B A square by L square. It is here. Eccentric loading, from this portion. And MFBD is plus WL square by WA square by B. WA square B by L square. So then substitute the values, and you'll get these moments 1 and 2. Okay, next, finding P1L, that is, because of the load which is applied, what is the rotation in 1 and 2 direction. Okay, now see here, P1L. Okay, 1L means in this direction, 1 means first direction. So from here, the moment is MF. If you write the formula, it is MFAB. So in MFAB, the fixed end moment is 0. So it is 0. Next, P2L. Okay, you can see it. This is in second direction, P2L. So P2L means it is connecting 1, 2, and 3. Three members are getting connected here. So that would be MFBA, MFBC, and MFBD. Okay, MFBA, MFBC, MFBD. Okay, add all of these. Then we get only, so first and second term are 0. Third term is 85. So write it here. So we got P1L, P2L. There are only two different coordinate directions. Okay, once you find out this, then find out P. So P is nothing but the external movement. Nowhere in A, B, C, or D there are any movements or rotations at the end supports. So because there are no movements at the end support, so P would be 0 and 0. And so in two different directions, it is 0. Okay. So once you find this P1L, P2L, P, next is you have to find the stiffness matrix. Okay. The stiffness matrix is given by, now what we'll do is apply unit displacement in coordinate direction 1. Okay, so you're applying theta is equal to 1 radian in first coordinate direction. That is, apply unit displacement at coordinate direction 1. That is, theta A is equal to 1 radian. Okay, so when you apply, first draw this diagram. Okay, first mark all the supports as fixed support, that is D, B, and C. Only release the support where you're applying the moment, that is the rotation. And here theta A is equal to 1. Okay, now theta A is equal to 1. So you have to always apply this theta in clockwise direction. So if you apply in clockwise direction, so what it does is it tries to push AB downward. So that's why here, if I apply load here, it tries to push AB downward. So that's why this is the deflected shape of the beam. Okay, all right. So now when you apply this load, there are two displacements getting created. Okay, so here also there is a displacement K1, K2 in this span of the beam AB. So you can see here, first I'll write K1, this is K2 because they represents the coordinate direction. K1 represents coordinate direction, K2 represents coordinate direction 2. Next, because you're applying theta A is equal to 1 in the first direction, okay, you're applying theta A is equal to 1. Theta you're applying in first coordinate direction 1, so it is 1. Here also, you've already written K2 because this deflection, this displacement is because of you applied theta A is equal to 1 in first coordinate direction. So K1, K2 represents coordinate direction. The next number indicates that is K11, K21, okay, because you're applying the moment in first coordinate direction. So it is K11, K21. Okay, so once you get this, next is as usual, you have to find K11 and K21. That is K11 is equal to, okay, K11 is this portion, that is MFAB. So MFAB is equal to, you have to put the slope deflection formula, that is 2EI by L. Okay, and A, it is starting from A to B, so 2 times theta A plus theta B. So theta A applying load, you have that is you're releasing the fixed end, so theta A exists, theta B will be 0, so theta A is equal to 1. So it is 2 by 2, 2 is a 4, 4 divided by 4 is 1, so 1 EI. Next, K21, K21 is this portion, so in K21 it is MFBA, so MFBA is equal to 2 EI by L, then 2 times theta B, 2 times theta B plus theta A. Again, theta B, if it's a fixed support, theta A is 1. Okay, so now it is K21 is 0.5 EI. Okay, so you found out K11, K21. Next, apply unit displacement at coordinate direction 2. Okay, the second condition now. In this direction, you have to apply the moment, unit displacement. So theta B, now this time it is theta B is equal to 1. So it's theta B is equal to 1. Now what happens is, B is connected to BA, BC and BD. Alright, so because it is connected to all three members, there is a deflection happening in all the three members because of the applied unit rotation. So now you can see here, theta B always, again, theta is theta B or theta A, always the rotations applied in clockwise. Okay, so this is theta B, will apply rotation in clockwise direction. So when I apply the rotation clockwise direction, what happens is, first thing is, it bends BC like this. Okay, first BC portion will bend. Once the BC portion is bent, only see here, you have to start from B to C, bend it, this portion. Next, again this rotation, it's tried to push BD this side, left side. So again this portion is bent. Then once it goes at this portion, okay, it's all clockwise. So first it will bend BC, then it will bend BD, then it will bend BA. So once again it pushes BA upward like this. Okay, it pushes BC downward, it pushes BD to the left side, and it pushes BA upward like this. Okay, once it pushes BA upward, Then it is like this, in this form. Okay, so now uh, all the three rotations are happening, all the three members are subjected to displacement. Okay, so now k 1 2. Okay, so k12 is equal to, see here, first what I'll do is the first coordinate direction, I'll write it as k1 k2, right? K1, and this is k2, first letter, first alphabet, sorry, first number. Okay, next, because I'm applying rotation in second direction, so it is k2 k12, and this is k22. Okay, all right. So once you mark this, next is find k12. So k12 is equal to mfab. Only this portion, k12, only this portion is moving. It is mfab. So again, it is 2ei by l, 2 times theta a plus theta b. But this time you're releasing theta b. So that's it, all other ends are fixed. Okay, all other ends are fixed. And theta b, only mark theta b. So this is zero point 0.5 ei remaining. Okay, then k22. Now k22 is nothing but mfbc, mfbd, mfba. All three you have to consider, because b is connected to all three members. Okay, so then mark this 2ei by l. So again, theta a plus 2 times theta b. So that is theta mfb. So it is mfba. Next, mfbc is 2ei. Again, be careful with the I value. So it is 2ei divided by l. Then it is theta bc. So it is 2 times theta b plus theta c. Then plus 2ei. Again, I value for this is 3i by l. So it is 2 times theta b plus theta d, 2 times theta b plus theta d. Okay, so then add all of this, then k22 is equal to, okay, 4.5 ei. Okay, now we have the stiffness matrix. So the stiffness matrix is given by k into delta is equal to p minus pl. So again, k11, um, k11, k21. Okay, now see, there's a little confusion. Again, I have um, always write this like this. So, okay, k11, k21 would be here actually, because see, the first number indicates the, because in quite a few textbooks, because they are same like this, so in few textbooks they have written it like this, that is k11 then k21. Okay, and this is k12 and k22, and luckily here it is equal, k21 and k12 are equal, so there is not a problem. But don't follow this, in few textbooks they have used this. Okay, even I have done this, but here it is easy, but you don't do this. The simple logic how to write this is, see here, k11, okay, it's like first row, first column, right? Next, here it would be k21, means second row, first column. Similarly here, k12. So k12 means first row, second column. K22, second row, second column. Okay, just switch this over. You should write this like this. K21 here, k12 here. All right. Hmm. Okay, then delta 1, delta 2 is equal to, okay, next p minus pl. So p is 0 only. Pl is, this is 0, and second is 85.33. Okay, next, take the common, substitute the values, take the common values here, and delta 1, delta 2, 0 minus 85.33. Okay, delta 1, delta 2 is equal to, again, 1 over ei. Okay, this should come here. So it is 1.5, 0.5, 4.5 inverse 0, and this is 85.33. So it's like matrix A, mat A inverse mat B. So here the delta 1 delta is nothing but theta A theta B. So theta A theta B is equal to 1 over A. Again I have solved this directly in the calci, because the calci it is already easy to solve. Again, I've already told you the procedure how to do it in the calci. So do it in the calci directly, put this as mat A inverse mat B. So theta A theta B. Theta A theta B. So MAB is equal to, substitute the value. Once you get this theta and theta value, substitute back in the formula. Now we have the formula for this is MAB is again the same slope deflection formulas. So same slope deflection formulas are nothing but that is if you want to find MAB is equal to MFAB plus 2EI by L, then 2 times theta A plus theta B minus 3 delta by L. Here delta happens to be 0 throughout. So no need to put delta. Okay, rest all will be same. Next, similarly MBA, same formula. MFBA plus 2EI by L, then 2 times theta A plus 2 times theta B plus theta A minus 3 delta by L. Again, put the formula, same slope deflection uh, formula, put the same slope deflection formula and solve this. Then you get MFAB, BA, BC, CB and BD and DB. Okay, now the check, you cannot have a check here because B is connected to three members. So whenever it connects three members, the moment will not be same. Only if it is connecting two members, the moments will be equal and opposite. So here no check as such. So you should just find BC, BD and BA. Okay. All right. So once you find out this, rest all, if you want, you can draw the bending moment diagram. Hmm. So drawing this diagram is very, very important. Okay. That is, you should know where the rotation is happening and how you should actually feel the behavior and deflection of the beam. Okay. You have to just apply some logic here, like how it bends, if it bends, where exactly, which beam bends first, which column, where it deflects, and how this portion bends. So once you understand this, rest all, drawing this is important. Once you understand this, rest all is just the simplification. Okay. All right. That's all for today. Thank you.